Hello, everyone. So let's start this session. I apologize for my voice. So I'm honored to introduce one of the ECC22 Semiplenary speakers. And I'm particularly fortunate to introduce John Ringwood. John studied in Ireland and Scotland. Despite this, his English, it's perfectly understandable. It's one of the clearest. And after his studies, he went to Dublin. He was an academic there for 15 years. And then he went to Maynooth University, where he was head of department there. And he started the department there, right, from scratch. He was also the Dean of Engineering in Maynooth University. And John is a reference point in our community for control of wave energy systems. In particular, in 2016, he received the IEEE Control System Magazine Outstanding Paper Award. And that paper, it's an amazing starting point if you're interested in this topic. After that, he received several other awards. He has more than 400 publications. He's associate editor for IEEE Transactions. And he also funded some startups, and some of these startups received national awards. So without further ado, let's give the word to John. So thank you very much.
Thank you, Giordano, for the lovely introduction, and thanks to the organizers for the invitation to speak to you. It's actually unusual for me to speak to a control audience, and quite a relief in some ways. Usually I'm speaking to hydrodynamicists, and then I have to cover the control side. So I think here it's going to be a little bit the other way around. And maybe I could start with a little bit of audience participation and ask you to put your hand up if you've ever seen a wave energy converter. Who has ever seen a wave energy converter? Okay, doesn't surprise me. Oh, one in the audience. Who has ever seen a picture of a wave energy converter? Okay, good. So certainly at the end of the talk, I'm hoping that the answer to the second question will be 100%, or at least it'll be a good indicator of who stayed awake during the talk. So it's probably a good statistical view of the degree of proliferation of wave energy. In fact, the degree to which people are aware of it. And even though wave energy has actually been around for quite a while, the first patents arrived at the end of the 19th century. But since then, the development and the acceleration in the development of the technology has sort of waxed and waned with the price of oil. So this talk is really quite high level. Just to check it out. And really it's going to focus on the application side. I guess I'm going to present probably more problems than solutions, and I'm hoping that I'm talking to a lot of people who are in the solution domain, and that you may have your own ideas, and I really look forward to bringing more people from the control community into the wave energy application area. Not sure. I can work with this, I guess. Oh, okay, thanks. Okay, so one of the motivations for wave energy as a renewable energy resource is that it's a complementary resource for some of the other renewables, and of course we're trying to aim for a zero carbon future. And to offset the use of fossil fuels, etc. And we have a high reliance on wind, but of course the wind doesn't always blow, and this just shows a picture of the demand, in fact, for the Faroe Islands, where there's quite a strong study going on, and it shows the value of adding on renewable energy from the marine renewable sector. Now it's not always the case that wave and wind are uncorrelated, and when waves are generated by local wind, they're highly correlated. But for example, on the west coast of Ireland, the waves come from storms and weather systems that are in mid-Atlantic. So there's actually quite a low correlation. And to minimize variability on the west coast of Ireland, we would have a mix of 30% and 70% between wind and wave. So it's predominantly wave. Wave and wind are both variable and unpredictable, while tide, for example, is variable but predictable. In terms of the amount of installed capacity, it's very low. I mean, the total global installed capacity is actually lower than 704 kilowatts is on the diagram here, because that doesn't include the systems that have been decommissioned. And even the aspiration in the future is not that high. I mean, 500 megawatts by 2030 is really only the size of a medium-sized power station. The important aspect here, though, is the cost. So the figure of 110 megawatt hours, 110 euro per megawatt hour would correspond to about 11 euro cent per kilowatt hour, which is about half the retail rate at the moment. And it would probably bring wave energy into a competitive line with, say, offshore wind. So onshore wind is probably a little bit lower than that. So really, it's about the cost of energy. Of course, the wave energy resource itself is free, but the cost of converting it is not. So it's really about maximizing and it's not an efficiency issue either. I mean, some people who work in this area get obsessed by efficiency. It's really purely a cost issue. So why is it so hard to harness wave energy? Well, the energy in waves is a mixture of potential and kinetic energy, and therefore there are a variety of principles that you can use to harness it. And it's not clear what the optimal harvesting principle is. It depends whether you're in deep water or in shallow water. And there is absolutely no technology convergence. There have been over 200 prototypes reported, and they all look a little bit different. One of the difficulties is that the energy flux is reciprocating. So at some stage, in order to use it usefully, we have to rectify that either at the hydrodynamic stage or the mechanical stage or the electrical stage. High force, low velocity, generally electrical generators like high velocity and low force. And also there are mechanical stresses, which often lead to over design as well. Unlike wind power, it's quite difficult in many cases to limit the hydrodynamic power impact on the device. So with wind, you can yaw the device or you can pitch the blades. With a floating device, it's quite hard to limit the impact of the waves on the device. And then there's a large variability in wave power. You can have a calm sea all the way to a force 10 storm. Finally, then the excitation that a wave energy device receives is across a range of frequencies. So all of this broadness or breadth of operational domain makes it quite hard really to get a device that can be well tuned to the local conditions. So as promised, here are some pictures of wave energy converters, and they all look a little bit different. So on the top left, we have an oscillating water column. So as the waves go up and down inside the chamber, they induce a reciprocating airflow through the turbine, and people have designed clever turbines that turn in a unidirectional way despite the bidirectional airflow. On the top in the middle, we have an overtopping device. It has a nice feature that the direction of flow through the turbine is unidirectional, so no other rectification is required. But for example, a 1 megawatt device of that type, which was deployed off the coast of Denmark, has got a 200-meter span and is really quite fragile. Top right, we have a heaving buoy, and it's a two-part buoy where one part moves relative to the other one with a loose mooring. On the bottom left, we have a flap type device, which is normally anchored in shallow water, and it uses the surge motion of the device. While on the bottom right, we have a hinge barge device where the central platform has got a heave plate to minimize its motion. And then we have relative pitch between the two end pontoons and the central device. I'll also mention, maybe give a special mention to this one. So this is a device which has really only been considered for the last 5 or 10 years, and it's a lift-based device. So it probably has characteristics closer to aerodynamics than hydrodynamics. And one of the things that makes it interesting from a control systems point of view is the number of different control actuators that you can use. So We can vary the generator torque, as we can with, in fact, most wave energy devices. But here we can also pitch the foil angles, and we can do that either to maximize power, but it also gives us a mechanism to spill power. We can also submerge the device by controlling DS, the depth of submersions. And finally, we can, on some of these devices, we can also change the radius. Now, some of these are fast control acting mechanisms and some are slow, but it gives us a lot of freedom to play with. So it's a 10-partner EU project. Our participation is on the control side, highly nonlinear system, but it's, again, one of 200 different prototypes. In terms of the wave resource, the wave resource is multi-frequency, and on the top right, you can see the different wave spectra that result from different winds. And we're assuming here that there's sufficient fetch for the waves to build up, and also that there's sufficient time for the waves to build up. So therefore, what we call a fully developed sea. But these wave models can be a little bit simplistic. So on the right-hand frame, you can see that we have that a wave model from a Pearson-Moscovich wave model, but it doesn't actually represent the sea state particularly well. We have generally got some summary statistics that describe these wave models. So H1/3 is the average of the 1/3 highest waves, and that actually comes from historical reasons from sailors' observations, and that's equal to HS, which is a significant wave height. And then there's a sort of a bulk measure of the period of the wave, or a representative measure, either TZ, which is the primary zero crossing period, TP, the peak period of the amplitude spectrum, or T, which is the peak energy spectrum. And there's an example spectrum, which is Brett-Schneider. So the challenge, and this is ultimately is the control objective, although it needs to be sort of distilled down to something that's a little more manageable, is to reduce the levelized cost of wave energy to compete not only with other renewables, with non-renewable sources, but also with renewables. And I guess the reason that I'm talking to you here today is that I believe that control technology has got a high role to play in reducing that levelized cost of energy. Generally speaking, this LCOE term here is distilled down to energy converted, which is something that's more tangible in terms of control objective, but we also need to be aware that the control actions that we take may also affect the operational costs as well. In general, there isn't a huge relationship between control actions and CapEx, other than the addition of maybe some sensors and actuators. And I guess maybe it trivializes things a little bit, but control is primarily a design exercise that involves implementation and software, maybe with the addition of some extra sensors and actuators. So compared to the capital cost of a device, which would typically be about maybe €1 million per megawatt, you know, the addition of control capability that's able to sufficiently improve the energy capture performance of the device is certainly something that looks appealing. So I'm going to cover a range of WEC models, wave energy converter models, from starting with the most complex and then come to something that's really very simple. So we've something to work with, and we're probably all aware of the immortal comments of George Box, and he's right. But I guess the important part here is the useful part, and there are a variety of uses to which we can put models to in the wave energy domain. So these are some of the different reasons that we need models. Certainly, project developers would need to be able to assess power production in a particular location to see if it's an economic proposition to put a wave energy farm there. Mechanical people need to assess loadings and forces under extreme sea conditions. And then we've a range of reasons to simulate the device. And they would particularly be fairly simple models because we put them in some sort of closed loop optimization strategy. And finally, of course, which is one of our main interests, is as a basis for model-based control design. And there is no sort of model that works for all of these things. And indeed, even within those categories, it's not entirely clear which is the best model. And models, of course, given the diversity of the wave energy converters themselves, are also diverse. Here are the various components in the powertrain that we could consider modeling, and it goes all the way from, as we say, wave to wire. we should probably also model the grid as well. And we can see here the different possible control inputs. One of the issues is that we have multiple changes in the form of power, and we may or may not have a hydraulic stage in here. So we may go directly from mechanical to electrical. Yeah, bond graphs are quite a nice way to model this. And of course, they have a close connection with Port Hamiltonian systems as well. Yeah, maybe just as something to keep in the back of your heads as we go on, this is sort of the simplest possible model or representation of a wave energy device that I'm going to work with. So here we just have a floating body. The power takeoff is where we convert the useful power. We can exert a control force F of U, and the device is subject to wave excitation Fex and has a velocity profile phi of t. So the useful converted power is mentioned in the PTO, and really this then forms something like our control objective. So we want to maximize the energy captured over an interval t. This is the sort of, these are the defining equations really for hydrodynamics. So they express conservation of mass and momentum via the Navier-Stokes equations. When we put a body into the water, or if we have a free surface and we have a seabed, that's described in terms of the boundary conditions for those equations. And there is no known closed form solution, although I remember seeing a film, Gifted, which was came out in 2017, and someone in that claimed to have solved the Navier-Stokes equations, but I haven't seen it published yet. We can solve these equations numerically by discretizing the domain one way or the other, and there are different forms of discretization, whether we go down the computational fluid dynamics route or smoothed particle hydrodynamics. So these equations are then used to describe the interaction between the particles, or indeed the cells within here, and both of them are very computationally complex. But we can simplify things a little bit if we just assume that the forces acting on the body are a linear superposition. We have mooring force. The radiation force is a force that experienced by the device by virtue of its own motion. So devices in motion generate their own waves, and that causes a hydrodynamic force. The forces due to the wave excitation include the diffraction force and the wave excitation force. And then we have a balancing force between buoyancy and gravity. And we may or may not have a viscous damping force depending on the nature of the device. And we get to choose the control force F of U. So with some more assumptions, which include that the fluid is irrotational, incompressible, and viscid, and we assume a small body approximation, which means that the wave elevation is constant across the whole body. And that's a reasonable assumption generally if the period of the wave is a lot longer than the characteristic device dimension. And then here's the really thorny assumption, which is that there are small oscillations, and I'll show you how they're really challenged in the wave energy domain. Then we end up with these expressions for these hydrodynamic forces, and of course we end up with these two convolution terms, and they form the celebrated Cummins equation. So Cummins equation was developed in the 1960s. And is really employed by most people who work in the sort of control area, simply because of its simplicity, but there isn't a simpler model available, in fact. We can simplify it a little bit further. Usually, instead of this convolution integral, we substitute that with a finite order dynamical model. And these quantities here, HR and HEX, are impulse response kernels that are produced in non-parametric form by one of these boundary element techniques here, and they can be produced either in the time domain or in the frequency domain. Eta is the wave excitation, so that describes the wave excitation on the device. And again, here's our control input here, F of U. This term here, M infinity, is an added mass term. So as the device moves, it carries an amount of surrounding fluid with it, which increases its mass. So that's where that comes from. And there are a whole variety of techniques to produce this finite order approximation, including one developed by ourselves. So one of the thorny issues really that make control or modeling, at least in the wave energy domain, a little bit difficult is the challenge of linearization. So if we look at this figure here, this is the sort of typical set point following a regulatory control problem. So we regulate a temperature, for example, to 18 degrees. We then linearize the system around 18 degrees. And what's nice is that the effort of the control system is always to drive it into that equilibrium point. So it seems quite reasonable to linearize about it, and the conditions for linearization are well honored. In the wave energy case, usually the objective of the device is really to exaggerate the motion. So you can see when the control is switched on here that we get quite an aggressive motion. So the concept of linearizing around an equilibrium point is one that's quite difficult. And in fact, the strange thing is that a lot of people, they develop models based on purely wave excitation, and then they subsequently use those for control design. And then the controller itself actually violates the assumptions under which the model was developed. So this is what I call the linearization paradox with wave energy. And you can see this maybe a little better in the animation here. So this is a particular sort of controller. I'll not go into the details of it for the moment, but again, you can see the difference between the device on top here, which is essentially just following the waves, while the one on the bottom has got, maybe just run that again. The one on the bottom has got a controller attached, which exaggerates its motion and much bigger variations in the wetted surface, and the operational space contained by the controlled one, of course, is much broader. So on the on the horizontal axis here, we have the relative displacement between the fluid surface and the device, and on the vertical axis, then it's relative velocity. So relative velocity, as it gets large, generally generates viscous drag, which is a quadratic nonlinearity. And then we end up with what are called nonlinear Fruchterloff forces, which are wave excitation forces as this becomes large. So with a larger operational space, we're likely to excite nonlinearities, which again is a challenge for both modeling and control. I'm just showing you a range of different modeling strategies here, with CFD being the sort of gold standard. So in terms of the computation and fidelity plane here, we have CFD here, which is the gold standard. And I'm not going to go through all these models in detail, just to mention that they increase, let's say, in complexity and in terms of nonlinear capability. But the important point here is to watch how they validate either under controlled or uncontrolled conditions. And under uncontrolled conditions, in fact, they all work pretty well. So in terms of fidelity, they have a fidelity close to CFD. But as we control the system, then most of the models fall away with really only this one approaching the fidelity of CFD. So in fact, by controlling the system and maximizing energy capture, we're creating a difficulty for ourselves. So this is, I guess, a picture that's familiar to everybody, but maybe it presents an alternative to getting around all these fundamental difficulties in modeling a wave energy converter from first principles. So to generate a database model, then we have the usual considerations, except I guess in terms of the experimental scenario, we have a few unique features. We can either use a numerical wave tank, which is based on CFD or SPH, or we can have a real tank where we can control the waves, or we can go to the open ocean. But in the open ocean, of course, we don't control the waves, and sometimes it's difficult to actually measure the wave climate as well. So then we can consider what sort of excitation, and again, this is a little bit unique to the wave energy case, what sort of parametric structure we choose for the model, and then how to identify the model. But the good news here is that generally speaking, because of the aggressiveness of our wave energy controller, and indeed the persistence of the wave excitation, good control, or indeed even in the benign situation, generally leads us to good identification. Whereas with a traditional control system, if we control it well to a set point, it means that it's quite difficult to identify. So in terms of the sort of data we can take from a system to identify the model, we can use the normal motion of the system under wave, or indeed put in our own identification signal via the power takeoff system. We can do a free response test. We can have a response just to some other wave excitation or power takeoff excitation, or have a combination of these. So here we can see the different ways that we can inject things into the system. So here we have eta is the free surface through the hydrodynamic model, then that gives us a wave excitation force, which adds on to the power takeoff force. And then we have the possibility again to change initial conditions. And generally, we're interested in the model here from the force input to the motion of the system. This shows the idea of rather than linearizing around the equilibrium point with the assumption of very small variation, is we could linearize around the equilibrium point, but not assuming a small variation. So we have what I call a representative linear model. And the example here is just from initial condition response tests, and you can see those here, although it's quite difficult to see how they differ from each other until you normalize the amplitude here. And then you can see that the ones which have quite a small initial condition variation, they ring a lot more than the ones from a larger amplitude, which are subject to much more damping, and that generally is viscous damping in the fluid. And if you look at the dominant poles of the system in the complex plane, in fact, this is the pink ones here are the ones that you get from this sort of physical modeling through the assumption of very small variations. And you can see that when you plot the dominant poles from these tests here, that they actually converge on this one as the amplitude or the initial amplitude gets very small. So that gives us the possibility to have a range of linear models that are good for different amplitudes, and we could either interpolate between those models or switch between those models potentially. This just shows, hopefully it's to work okay. It shows an example of a test that we did at Aalborg University last September by a team from the nuclear and basically what it is a down chirp test. So the leg of the platform you can see here, and this is a floater. This is a linear generator here that we're able to both use as a motor and as a generator. And we start with high frequencies. So we do a down chirp, and the reason we do that is because small frequency waves generally have a much longer reflection time. And this is a big issue in wave tanks. Wave tanks normally have wave cancelers either through the wave makers themselves actually work as wave cancelers, but also there's usually some sort of a beach that kills the waves as well. But inevitably you do get contamination from reflections. So you can see here as we start in high frequency, really there's very little reaction in the device. And then as we go down in frequency and we start to approach the resonant frequency of the system, you can see that we get a much more significant response. And then as we get right at the resonance, then we actually get overtopping of the device and quite nonlinear sort of behavior. And the sort of responses that we get from this then are documented here in a bug plot. So you can see that they're documented for different amplitudes of chirp signal. So we get a spread, and they're useful for different sorts of control design, including a version of a robust control design that we've done, which is based on the best worst case analysis. But also it also feeds into another form of controller that we have as well that I'll show you. So on to wet control then, and I'm going to start with the very basics, and some of this may be obvious to some of you, but maybe not all. In terms of the objective then, as I mentioned, the really high level objective is to minimize the levelized cost of energy. But again, that's usually distilled down to maximizing energy absorption over an interval t. Power is given by the product of force and velocity, and energy is the integral of that. And of course, the system has got some real physical constraints, particularly in terms of displacement. It usually has a finite stroke length if it's a heaving buoy. It may have velocity constraints as well, and there's definitely a maximum force that we can induce with the power takeoff as well. And then finally, there's a somewhat unique constraint that we might need to apply as well, which is this one here, which is a constraint on reverse power flow. And you can say, well, why would there be reverse power flow? I mean, surely we're trying to harness energy rather than put energy into the system. But it turns out that even for a simple harmonic wave, that there's a period of that wave that if you inject some energy into the system, you actually get more back. And it's very similar to what a child or indeed an adult does on a swing, that you kick your legs out at one point in the cycle. And the timing of that is absolutely crucial. And by putting that energy into the system, it then sustains the motion. And the reason we would put a constraint on it is sometimes these reverse power flow peaks are actually higher than the rated power or the forward power capacity of the system. So that's why we need that constraint. Okay, so in terms of the fundamental contributions to wave energy control, they arrived in the 70s from the likes of Stephen Salter at the University of Edinburgh, and Kel Bidal and Johannes Valnes at NTNU, and David Evans from the University of Bristol. But it's interesting that, I mean, Stephen Salter and Kel Bidal, Johannes Valnes were all from departments of physics, while David Evans was an applied mathematician. So there's certainly ample opportunity for control people to get involved and to look at this in a concerted way. Their initial focus was on monochromatic waves, and there are all sorts of parallels, in fact, because we're dealing with resonating systems in AC circuit analysis. And in fact, at only a workshop in Torino 2 months ago, somebody reinvented the Smith chart. So those of you who have an electronic engineering background will be familiar with the Smith chart from electrical transmission lines. But this guy who had his background really in hydrodynamics had no concept of it, and reinvented the wheel in a different domain. And it's not unusual in the wave energy community. And also, in fact, recently we've discovered close connections with tidal barrage control. Maybe that's not unsurprising because they're both driven by harmonic excitation, although the timescales are quite different. So with Cummins equation then as a start, let's look at how we might control a wave energy converter. So we take Cummins equation, we express it in the frequency domain, which is in equation 12 there. And you can see the terms involving the radiation, mass, added mass, and then the buoyancy term. And this is termed the intrinsic impedance of the system. So it's similar to what you would imagine in an electrical circuit as the internal impedance of an electrical system. And it's a mechanical impedance generally, and it's the ratio of force to velocity. And any of us who certainly have done basic AC circuit analysis know the answer as to how to maximize power conversion or power transmission from this system, which is the wave energy converter, into the load, which is where the useful power is. And that's by choosing the load as the complex conjugate of the intrinsic impedance of the system. So that's a simple choice. We can formalize that then in a feedback structure. And indeed, we can parameterize the power takeoff force, in fact, in terms of similar quantities that we have in the model. And this looks very like a PID controller. And indeed, it is the most ubiquitous controller in wave energy, in the same way that PID probably is in the more general control community. The difference is that the controller is not driven by an error, but it's driven by velocity. So if we then choose the complex conjugate, and you can see that the controller impedance is expressed by these terms here again, involving these hydrodynamic coefficients. To get the complex conjugate, we really just need one real and one imaginary value. So we don't actually need both of these, and we can choose which one. But what it does is it gives us a nice visibility into how we can do control co-design. So in fact, if we want to change the mass of the system, or we want to change the damping in the system, we can do that either with the physical system, or we can do it virtually via the controller parameters. Of course, as we vary these things, it may have implications for the maximum power takeoff force. We need to be a little bit careful about that. Okay, so that's a basic controller. The problem is that it only works at a single frequency. and it doesn't give us any ability to handle the constraints that I mentioned at the start in relation to displacement, particularly, and force. So we develop what we call this LightCon controller, which is it's a linear time invariant controller, so it's a fixed controller. And what it does essentially is tries to determine the complex conjugate of the system across the whole frequency range. And that ideal controller is the black one here, which in fact is unrealizable. So the closest realizable one you can get is this blue one here. And then with this controller, we can also put in a constraint handling mechanism because it's got this feed forward structure here. And you can see what happens as to the frequency response as we vary that. And K, this free parameter here, which helps us to do constraint handling, is based on some real-time wave statistics. Now, one of the difficulties is that you can't implement this multi-frequency impedance matching controller in a feedback form. It's consistently unstable. So we have to use the feed-forward form. And the difficulty with that is that we need to know the wave excitation, which in fact is not only, well, it's an unmeasurable quantity. There is no sensor that you can build to measure it. So it has to be estimated, and there are a variety of estimation methods we can use, including Kalman-based estimators. Sorry. Oops. So this just formalizes the feed forward structure. So the first controller structure, the feedback structure, is called ACC, or approximate complex conjugate control, while this is approximate velocity tracking. And this structure gives us a lot more freedom, especially in how we can manage constraints, the sort of models we can use, but it does come with the disadvantage that we need a measure of the excitation force. So there are two parts to the control. Then we have an estimate of the excitation force. We solve this control problem here to determine the optimal velocity reference, which is going to capture the maximum amount of power. And then we use the controller K2 to make sure that the system achieves that velocity reference. Yeah, there are a variety of ways now that we can design K1. And one of the ways we can do that is via numerical optimization. And of course, we can use constrained numerical optimization to recognize the constraints in the system. And the only difficulty is that as we implement this in a sort of receding horizon fashion, then we need future values of the excitation force. So not only do we need to estimate it, but we also need to forecast it into the future. Okay. So one possibility, and there are quite a few examples where people have applied, let's say, a somewhat traditional MPC type controller in a receding horizon fashion to the wave energy problem, of course, using a different objective function. So it's not an error tracking or an error minimization controller. It's trying to maximize this energy function, which actually ends up being a non-convex problem in the fundamental way when expressed in an MPC form. So one of the things we looked at is maybe transcribing the problem into a different space using some basis functions. And we recognize that most of the signals in the system are harmonic or multi-harmonic. So it makes sense to use those type of basis functions that might allow us to operate in a different parametric space. And here we just show a sort of a sample wave signal, or it could represent velocity or displacement within the system. And we've arranged a different functions that we can use to approximate that. The zero order hold one is the blue, and of course, as the sampling period gets very short, we get a good estimate, but then our computation goes up. And if you look at the fit that we get for a number of basis functions, these half-range Chebyshev Fourier functions seem to work very well. Fourier functions we can use as well, and they can work in some instances, but of course we get discontinuities at the leading and trailing edge of the prediction window. In terms of the performance of these type of transcribe problems and solved in that domain versus more straightforward MPC, we generally get at least as much power captured. But the most important thing is we've reduced the computation by a factor of 3, which is very useful if we're doing online optimization. And in fact, working with people in Imperial College here, including Giordano and Alessandro, we've utilized the moment domain to great effect. So one of the key moves in the moment domain is the signal generator here, and we can choose that signal generator to best match the nature of the signal. So again, we can choose a harmonic signal generator, and that provides a nice integrated framework to solve the problem. And importantly, what might be seen as a restriction of just dealing with the steady state response, but in fact that suits us very well in this application because we're not really interested in the transient response. And yeah, I can show you controller in action. So again, you can see quite an exaggerated motion. It's not as discontinuous as the first animation I showed you. And most importantly, we're able to keep the displacement and the force strictly within these limits here. And also one of the important aspects is that the problem is now a convex problem. And in fact, the problem is convex also for certain. We've also solved the nonlinear control problem for certain classes of nonlinearity, and also that's a convex problem as well, which is quite important. And here we have a tank test of. Maybe difficult to see exactly what's happened, but what's happening here. But on the left-hand side, we have the free body with just no control force attached. And on the right-hand side, we have the moment-based controller. One of the important differences I just want you to see is that the phase of both of them is really quite different. And of course, in the control case, we can respect the system constraints as well. So the one on the right-hand side is maximizing the power capture, and the power takeoff is in this linear motor up here. Again, so for some of the stroke period, we're actually putting energy into the system, but overall that gives us more energy back. Okay, so in terms of a framework, the moment domain has really proved fantastic for us. I mean, not only can we do control, but of course, you know, I guess in terms of the group in Imperial College, it's been popularized in terms of this ability to do linear and nonlinear model reduction. So we can do linear and then a nonlinear control based on those. We can do some robust control. We have a receding horizon implementation, and we can also extend it to the control of arrays. And currently we're working on constructing estimators and forecasters within the moment domain as well. So the business of estimation and forecasting is not quite trivial, but it's not impossible. I mean, there are two ways, well, there are a variety of ways of building estimators, and they're documented in this reference here. And in terms of forecasting, then we've two options. We can either make some upwave measurements here using data buoys and anticipate what's going to happen on the wave energy converter. We then need a model, of course, for the propagation between the two locations. Or we can just try and estimate the excitation force from measurements of the device motion and use it as a sensor. And that's really the most popular one, and certainly the simplest one as well. I mean, we have compared both in this one here, and there seems to be very little added value in doing that, at least for a wave energy converter that was commissioned on Pico Island in the Atlantic. And yeah, I mean, we've constructed what we call an optimal forecasting framework under the assumption of Gaussianity that tells you that if you want a certain amount of prediction horizon and you want that at a certain fidelity, that you have to put wave sensors in the water at certain locations. Yeah, but finally, I mean, you know, in terms of forecasting, the autoregressive model actually seems to perform really quite well in this application. Now, a lot of people might imagine that in renewable energy, you know, it's an obvious candidate for extreme seeking control because, you know what you want to, your target is, which is this energy function here. So you just measure the energies coming out of your system, and then you adjust the control on the basis of that, and you forget about the model. And indeed, it works quite well in some applications, for example, in solar PV. But the difficulty in wave energy is that the wave statistics are such that it takes quite a while to get a statistical measure of what your control is doing over all those frequencies. So here I just showed the performance function evaluated for 10, 100, and 1,000. Call them peak waves. They're sort of pseudo peak wave periods. Remember that the wave signal is panchromatic. And you can see that, you know, until you get to something like 100 peak wave periods, it's not getting to a sort of a searchable state. And of course, we want to control the system not only wave by wave, but also intra wave. So we want to control it second by second. So this really is quite a challenge, given that we can only really get a decent performance function evaluation after a period of time. So it's, I guess, an ongoing piece of work, and it's an area that we could certainly use a lot of help with if anyone has any ideas. Control of wave energy converters is an important one, because the same as wind farms, commercial deployment of wave energy will be in farms. But unlike wind farms, where only generally destructive interference happens, in wave energy converters, they can actually generate favorable radiated waves, or waves that are favorable to other devices in the array. So you can have both destructive and constructive interference. So all the devices then effectively are actuators in terms of generating these favorable waves, and all of the devices are basically a set of sensors as well to be able to work out what's going on. So this is just a simple example here of a triangular array. We have a consistent spacing D between the different devices, and we look at the ratio of the control harnessed with a set of independent controllers to a global controller. Now, as the spacing becomes very large, the radiated waves, particularly from circular devices, diminishes very fast, because, of course, the wave energy is consistent, but as the circle of the wave increases, the energy density decreases significantly. So beyond a certain point where the spacing relative to the radius of the devices is about 10, there isn't a whole lot of difference. But certainly, again, it's really the overhead is a bit of communication and a little bit of extra control implementation. Just a few words about sensitivity. There are multiple sources of error, uncertainty, certainly in the models, and I think hopefully that's clear from the earlier slides. The assumption of small oscillations is really challenged again, because our control is trying to exaggerate the motion. We often ignore viscous effects, and linear excitation and buoyancy forces are okay for some devices that have a fairly uniform cross-sectional area. And then, you know, numerical errors and other errors associated with mesh-based, not only CFD, but also the boundary element hydrodynamic type calculations. If we're going to take data and determine models from that, we have limited resolution of that data, both in terms of the measurement accuracy and in terms of noise. And then some other modeled, unmodeled, particularly hydrodynamics. And then there's also a limit, obviously, to the complexity that we can endure both computationally and analytically in determining wave energy controllers. So maybe just as a first stab, just take a look at the closed loop system sensitivity, and this is a familiar looking term for a lot of people in the community here. And generally, what we try and do through robust control design is we try and make the product GH large at either one or a range of frequencies, and if we can make the loop passive, then we can increase the gain and reduce the closed loop sensitivity. So normally we would expect the closed loop sensitivity to be far superior to the open loop sensitivity. We could also calculate the sensitivity to each of the individual terms, which include the mass, damping, and spring. So we can look at sensitivity to particular errors in those hydrodynamic coefficients. And it's a little bit scary. These are all positive numbers here. So in fact, the sensitivity function is actually worse than the open loop sensitivity at most frequencies. The only frequency that looks vaguely reasonable is this frequency here, and that happens to be the resonant frequency of the device. But if you have the wave frequency, which is here, at the resonant frequency of the device, in fact, there's nothing for the controller to do. So the controller is actually inactive at this frequency, and otherwise, the sensitivity function becomes quite large and a little bit worrying. But yeah, so this is what I call the third paradox. In general, when you put a closed loop controller on a system and you have some freedom, at least in the choice of the feedback, you can improve the sensitivity properties of the system. The problem here is that, just going back to the sensitivity function, the relationship between G and H is pretty fixed by virtue of their complex conjugate relationship. Okay, So maybe there's an alternative metric that's a little bit more important. And so we start to look at what's the effect of those errors or relative errors, let's say, in either the real or imaginary part of the intrinsic impedance on the power production capability, because that's what really matters. So we look at the percentage error in the real terms, which would be the radiation damping, and then the imaginary terms, which would respect inertial or stiffness errors. And then we calculate the ratio of the actual power produced under those perturbed conditions to the nominal case. And there are, we have also, as I mentioned earlier, some robust control results for these devices as well to mitigate the effects of these. But let's take a look at the sensitivities in power production. So we look at two controllers, the approximate complex conjugate feedback controller, or the approximate velocity tracking, which is the feed-forward controller. And for relatively small errors, then we see that a 10% for the ACC controller, a 10% error in the damping term would lead to just a 0.25% change in the power produced, which is quite nice. And in the AVT case, it's a little bit worse. And in particular, looking at the AVT case, which is the blue line here, you can see that, in fact, negative errors are much more costly than positive errors. So if you're going to, if there is uncertainty in the damping term, and you're going to use an AVT controller, you're better to overestimate it than to underestimate it. In terms of inertial or stiffness terms, it turns out, in fact, that the AVT controller is completely insensitive as far as power production goes to those errors, while the ACC controller is super sensitive. So you can see that at a particular, I've just shown 3 different wave frequencies here, 7, 9, and 12 seconds, bearing in mind that the resonant period of the device is 9 seconds. And when the resonant period of the device is the same as the wave frequency, then this sensitivity doesn't look too bad. But once you move even slightly away from that, and this goes in both directions, both when the wave period is longer and shorter than the resonant period, you get a very quick drop off here in the power produced. So the penalty is quite large for inertial or stiffness term errors as far as the ACC controller is concerned. And then finally, with regard to excitation force errors, of course, the ACC controller doesn't need an estimate, so it's completely insensitive to those type of errors, while there is, let's say, a moderate sensitivity in the case of the AVT controller. Okay, so to finish off then, so wave energy shares a control objective with other renewable energy sources, and particularly it's trying to reduce the levelized cost of energy. Again, the resource is free, the cost of converting it is not, and control technology can play a major role, I think, in reducing the levelized cost of energy. But levelized cost of energy is not a good end in itself. I mean, you'll have heard numbers quoted, like, for example, when someone installs a new wind farm, they say, oh, this is going to power 10,000 homes, and they'll do that on average. But at any point in the day, it may be that they actually don't generate any electricity at all. So this is the concept of value of energy. And this is hopefully where wave energy can be of use in being a complement to other renewable energy sources. As we've seen, the whole issue of linearization, and we all like linear models, is impaired, in fact, by the use of control, which is uncharacteristic generally of control loops. There's a variety of control solutions. I've only shown you really the outline of 1 or 2. They have various advantages and disadvantages, and they also may be unique or customized or need to be customized for various devices. And then we have an unknown input estimation problem, and also a forecasting problem, especially if we use the AVT controller, which gives us a lot more flexibility in dealing with constraints and different sorts of models. And also, we discovered a significant interaction between the control design problem and the device or array design problem. So it turns out that the optimal geometry for a device is highly dependent on how you control it. And also the optimal array layout is highly dependent on how you control it. So it's very much a two-way interaction between the system and the control. And it's my firm belief that there's huge opportunity to use other methods from what I call traditional control technology space. And indeed, people that work in other application areas, I'm hoping that you may have seen something here that sort of, lights up a spark somewhere, and you can see some opportunity to migrate it to a different application area, because I think there really is huge opportunity. And also opportunities for young researchers to get involved. For ourselves and other communities, we have, we've PhD and postdoc positions available. And with that, I'll thank you for listening. And if you do have any ideas, please do not be afraid to contact me at this email address. So thank you.